So once the mathematicians realized that we could find out how far an object traveled by looking at the region and finding the area of the region under the velocity curve or the velocity function, they started to explore further and say, well, what if it wasn't a perfect geometric shape? What if instead of having a rectangle or a triangle or a semicircle, we had a function a velocity function which varied with respect to time, okay? What if our marathoner started off at one pace and then slowly increased her velocity as she was moving into the middle of the run and then started to tire and then the velocity began to decrease? Is the area of this region still equal to the total distance that she traveled? That was the next question, right? What do you think? Does this blue region right here still represent the distance that she traveled during her 2-hour run? Seems like it, right? And that's what our mathematicians, that's what Newton and Leibniz really thought, that was the case. But they didn't have a geometric formula for this shape right here. They had rectangles, they had triangles, but they didn't have this curve right here. So what should they do? How do we get this area? How do we figure out the area and therefore figure out the distance that the runner traveled? Right? And their solution, even though they didn't really formalize it, was to kind of approximate this area, saying, you know what, this isn't a perfect shape, but what if we just drew that horizontal line right there, created a rectangle? All right, now if we found the area of this rectangle, yeah, we'd have an issue because we'd be missing this zone up here where we're definitely too small. We've got some kind of underestimate going here, but at least it's a starting point to get us how far she traveled. All right, and you know what? We could do another estimate which hits the peak, like so. Okay, now create the rectangle. That rectangle is too large. Okay, so it's almost like Goldilocks in the Three Bears. We have one rectangle which is too small. We have another rectangle which is too large. Perhaps we could find a rectangle, right in between that would take some extra area and miss some other area and get us our certain value. Or perhaps even better, what if instead of having one rectangle, we improved our issue by having two rectangles? All right, now we can have one rectangle, which, let's get rid of these for a second. All right, we could have one rectangle, perhaps, which takes care of the first half of our zone. All right, this one could be a little bit too large. And then the second rectangle could take care of the second half of the zone, and maybe this one is a little bit too small. And now we have a better idea because we can kind of average, or we can add these two areas up and it'll get closer because we have two rectangles to work with instead of just one. Right? This is where they started to attack the problems and say, well, if we did one rectangle, can we do two? If we do two rectangles, can we do four? If we can do four, can we do 40? And this was eventually all put together and termed a Riemann sum.